Good afternoon. My name is Xiaowei, and I come from Chinese Academy of Sciences. I'm very glad to be here to give you a presentation, of which the title is Forecasting Task Optimization for a New Architecture of MEMS Variable Computing with Stiffness Modulation. I'm going to introduce these four parts. First one is the background. And with the booming of the Internet of Things in our information-driven society, massive raw data generated from thousands of sensor nodes are consuming more and more transmission capacity, which calls for the system ability to process information efficiently with low power consumption. Therefore, localization of signal processing is highly desired, as sensing and intelligence need to be integrated, achieving edge computing. So, reservoir computing, which is called RC, it is generated from recurrent neural networks. It has the merits of easy to train, high accuracy, and suited for time series tasks. And what's more important is that it can be easy to hardware implemented. Why is that? Because the core concept of the reservoir computing is that it only has three layers. The first layer is input layer. It is randomly fixed. And the second layer is the reservoir layer. It is a randomly sparsely connected neurons. And the third layer is the output. It is only a simple linear regression. So because the structure of the reservoir is unchanged, no adaptive updating is required. So it is easy to use a physical device. It's the nonlinear. Oh, sorry. Yeah. So this one. It is easy to use a physical system to use the reservoir. And MEMS takes advantages of small volume, low power, easy integrated, and among which the most important that it has the characteristic. Oh, sorry. It has the characteristic of nonlinear and fading characteristics, and this characteristics is very needed for the MEMS RC. So and also the MEMS is designed for sensing. So MEMS RC is more closer to the initial intention of edge computing. But the traditional MEMS RC uses this amplitude modulation mode. This is that you have to collect the data as voltage before you input into the reservoir. So you need ADC or DAC and delay loop. So we only use the MEMS as a computing unit in the formal. So it cannot integrate the sensing and intelligence. So our work uses the stiffness modulated this mode. So we directly injected the data as a natural signal after it is being sent by the MEMS, like this. So we use the stiffness disturbance, and the data discretization is only at the output layer. So this work primarily achieves the sensory and computational fusion. And the second part is the theory of our stiffness modulated RC. So firstly, I'm going to introduce the nonlinearity. Both of the two modes uses the Darfing nonlinearity as shown in these functions. And but the data input is different. As you can see in the amplitude motion, the input is the input UT is input by a mass MT, and it is modulated to the electrical force. So it needs a transduction between the mechanical force and the electrical force. So we need so the system is complex. But in our stiffness modulation, the input is directly injected into the photon. So then this input will influence this is the stiffness of the resonator. So this is directly result of data discretization. And in detail, this is a figure of our stiffness modulated RC. And the structure is shown in this figure. We used differential MEMS accelerometer. This is a resonant accelerometer, and the top resonator is for sensing, and the bottom one is for computing. And basically, the detail RC is here. So we use DC bias and an AC drive, and then we collect the response by TIA and local splitter, and then it is collected by an ADC, and then the data is post-processed. The wider point of the RC is dynamics of level. So as this figure shows the step down and step up of the amplitude and acceleration curve. So we almost use this validation point like this. So when the resonator is operating, we have to keep the operating point among this yellow region. So why our mode is more better than the traditional mode? This is because not only because we have a more unique nonlinearity as from before, but also our stiffness modulated can distinguish between this bidirectional data. As shown in this figure, the input is a series of 1 and -1. The response of the amplitude modulation cannot divide it very well. This is because the amplitude modulation take the absolute value of the input. But in our stiffness modulation, we can divide it very well like this, and also it has a richer nonlinearity like this. So, and as our title is about the forecasting optimization, why we need this optimization? This is because when we simplify the physical structure, as we can see from A to B, this is our Paris word. The longer, because we simplify the physical reservoir, so the long-term memory capacity is discarded to some extent. This is because we eliminate the delay loop, and also we eliminate the mask operator like this. But we know that our non-delay based MEMS RC proposed before is also the digital to analog and then digital. So it cannot it cannot generate it cannot process the natural signal. But in our this work, we use this stiffness mode because then we can use this input and reservoir layer. This is all analog in the green analog area. So the physical part is directly and simple. And our optimization is software that we remove the delay loop and the mask to the output layer like this. And also we add three more nonlinearities. This nonlinearities is like this. And thus, this is good to catch the interested feature of the test. And the detailed algorithm, you can refer to my paper, and I cannot explain this so explicitly right now. And the third part is the experiment. As we can see, this is the system design. So the diagram of the differential MEMS accelerometer is shown in figure A. And I have introduced about the two resonators. But you can see there are four or six on the diagram. The COM drive in the middle is for virtual accelerations, which will be explained next. And we focus on the bottom as the sensing one, the top one can be connected to our closed loop AC. The RC system is here, and the real circuit is C. And our setup is shown here. Basically, it is the same as we shown before. And I have to say that the home drive is connected to another DC power like this. So it will bring an electrical force to simulate a virtual acceleration. To simulate the virtual acceleration force, and then you can add a virtual acceleration to this resonator. So we have these two kinds of setup as shown in figure B and figure C. One is for the test, and the other is for the calibration first, which we use a tilt table to generate a real acceleration. And we show the calibration curves of these two types. We can see that there's a little bit, and yes, we eliminate the fit through in our circuit. And we know that virtual acceleration is equal to the square of the ABC. And by fitting, we get the parameter of 1 to 100. And with the calibration, we have these two scale factors. They are almost the same, but we have to take it into account when we add the acceleration which reflects our task. And we also increase the voltage, and we can see the nonlinear curves like this one. This is also sweep up and sweep down. Sweep up is this and sweep down is this. And but when operating, we have to see in this figure, yeah, because we want to use the amplitude and acceleration nonlinear. And also we have to make the resonator operate in this yellow region. And the fourth part is our result. We show the result of a very complex Llama 10 task. This is a task related to a chaotic system that each time point is related to at least 10 previous points. You can see on this one. And when n equals to 10, it is a Llama 10 task. And so it is very difficult to forecast the next point. So a normal network without long-term time dependency cannot deal with this deal with this task. And our results show and after being processed by the resonator, we can get an HD. And each time point is this red circle. And this is the reservoir state when we produce this point by the mask operator and delay loop. And also we add 3 more nonlinearities. Also we acceleration them together, so we get this space vector. And so it is then multiplied by a weight vector. This weight vector is around 331 points like this. And then you can get the ground truth and the output. There is comparing in this figure. And also in this figure, this is different points. And I have to mention that there are 2 vital parameters relating to the time. It is theta and tau. The theta is the physical time that relating to the ADC, and the tau is related to the numerical one, which means that if you increase the tau, the data is more slower to inject into the RC, and the tau is related to this from the mask operator like this. And we also sweep the length of the delay length of the delay loop to this end. And so we sweep this one and this one, then get this. We evaluate it by the normalized square NMC. Yeah, normalized mean square error like this. So and we also compare to our previous work and the optical RC. So shows the priority of this work. It is a relative improvement. And there are some conclusions. Why our system is better? I think that there are mainly two topics. At the hardware level, because our MEMS is more sensitive to mechanical signal, so the data is more pure without the transaction between the mechanical and electrical. So and another one is there's a richer reservoir physical reservoir by our nonlinearity tuning. And at software level, we optimize the output layer, so it brings the long-term memory capacity. And also because our delay loop and the mask is generated by numerically, so it is has a less noise. And also this kind of operator will regain the high dimensional by the mask. And our future works will focus on the topology of our sensors. Maybe we can use these lines or columns of the resonator to simultaneously to process some tasks like this. Okay, thanks for listening.